everybody. The purpose of this video is to get you an understanding, I hope, of something we were talking about in class. Let me stop that from wiggling. There we go. So in class, we've been talking about this wonderful bell curve for a while now, and we've been learning some areas that are contained in certain regions of this curve, and you've been wonderful. You've taken my word for so many of these things and believed me when I've told you that, for example, there's 68% of the curve between -1 and 1, and there's 95% here, and you've been really, really good at believing me, and I've challenged you recently to kind of not believe me so much. Now, my hands are a little bit tied because in addition to me telling you that, I've also told you repeatedly that there's a problem with knowing how to find those areas, because those areas can only be found using the ideas of integral calculus, which is what I want to get at with this video without doing the calculus. I want to lean on two things: geometry and technology, both of which come in real handy when you're doing calculus, especially of this kind. So if you've had calculus before, some of what we're going to talk about here is going to make sense. If you haven't, I think it'll still make sense, because this part of calculus, just like most of calculus, is not really new math as much as it's old math looked at a different way. So anyway, what I want to start with, before we go anywhere else, is I want to make sure that you understand how the equivalence exists between the area under this curve and the sum of all of the probabilities in a distribution. We know that that has to equal 1. We've been over that a bazillion times in class. But in class, we've had discrete distributions where you had an x column and a p of x column. And they were very discrete. You could actually look at each one of those individually, add them up, and they're 100%. With a continuous distribution like the bell curve, I've thrown a couple of these things called z-scores onto the axis: 0, -1, 2, 1, 2, 3, and so forth, representing standard deviations from the mean. The problem is there's infinitely many values, -1 to 0, for example. In a discrete distribution, that would be it. -1, next one is 0. But in a continuous distribution, there's infinitely many numbers. We had this discussion in class, as you remember. So it becomes a challenge to figure out, okay, so this one's -1's probability actually lives here. 0's probability actually lives here. But the thing I alluded to in class was, what does here mean? So what I want you to realize is there is a second axis over here, which would be the probability axis. So in a t-table, like we've been looking at in class, the t-table, the probability is the right column, which would, if you're thinking about like algebra classes, it's like your y column, your x column and your y column. Well, here's your x or z column, your data column, and your probability column is represented as another axis. Now, as it turns out, this beautiful curve has an equation, and the probabilities that are on that axis are given by this gorgeous and not to be worried about equation. 1 over √2 pi times e to the negative, we'll call this z squared over 2. So if you know the z-score, whatever z-score is down here, if you plug that z-score into that formula, you are given the height of the curve at that point. So you can plug in 0 to that curve and figure out how high that is. I'm going to do it for you in a little bit here. You can plug in -1. You can plug in 1. What's kind of cool about that equation, actually, is you can see what happens, why -1 and 1 have basically the same height. Since z is squared, it's a symmetric distribution around 0. So that explains why the curve is equal left and right side. Kind of cool, kind of cool. The e here explains why you have a bit of an exponential nature to it. The squaring of the z gives you the symmetry result, the pull down and then tail out. But what I really want to do is I want to use this curve to explain to you how to add up the probabilities of all of the data values on these axes. So you got to realize, of course, that when I say all of these data values on the axes, there are infinitely many of them. So you might wonder to yourself, how do you do that? Well, some very clever folks back in the 1700s, and one in particular, Riemann, gave us the idea of approximating this curve, or any curve, by breaking it up into small pieces and then counting those pieces. So here's something Riemann may have done. He said, okay, I know there's infinitely many values between 0 and -1. What I'm going to do is I'm going to put a point up here, right? And what that point would be, and I'll get this for you momentarily, is if you plug 0 into that equation, you'll get the height of this point. And then -1 would be here. And if you plug -1 into that equation, you get the height of that point. And what Riemann figured out was, if I have the height of that point, I know how long that line is. And I know how long that line is if I plug 0 in. And I know that this, which is at right angles to the base, has length of 1. If I connect these two points with a line like that, I've formed a trapezoid. And that trapezoid makes up a pretty good chunk of that section of the curve. It's missing a little bit right here. It's missing this little, whatever you want to call it. And then he continued to do the exact same thing on both sides. Okay? And then the same thing at 2. And the same thing at 3. And continuing on and on and on. Same thing at -2. The same thing at -3. And you can see what happens. Sometimes the line will go above the curve. Sometimes it goes below. But his point is that eventually you get quite a bit of the curve all added up. And I'm going to stop from -3 to 3, and we'll come back to that too later in the video. It obviously will go on forever, but I'm going to run out of board pretty quick. But what I'm going to do right now is I'm going to speed the video up, and over the course of me speeding it up, I'm going to do some math up here. I'm going to do the area of these 6 trapezoids. I'm going to figure out what those are by plugging these numbers into that equation and running some geometry. You might remember, I don't know if you remember or not, but the area of a trapezoid can be found by taking the average of the bases and multiplying by the height. So I'm going to use that formula, and I'll come back to that once I run the numbers, and I'll show you what I got there. But I'm going to go ahead and speed up the video and run these numbers for you. So just hang tight, and you'll see me kind of like running around like this, and I'll get the numbers for you, and we'll regroup right here, and we'll figure out what's going on. Cool. I'm going to pause here for just a moment, and then I'm going to get back into the math. What I was able to do was, this is by sticking each of these values into that equation that gives you the height of the curve at those points. I don't want you to get too lost about those, because some of you might be thinking, wait a minute, if this is 40% likely, and that's 24% likely, and that's 24% likely, and those are 5% likely, if I add up those numbers, that's getting too close to 100%, and there's still infinitely many in between. For those of you that are that concerned about it, I encourage you to take a calculus class to explain away the concern. I don't want you to focus on that. This is pure mathematics, not applied to statistics right now. You're about to see how we're going to use this by doing the geometry, because now I know the bases, right? I have these bases in the trapezoid. All I got to do now is multiply by the height, but the heights are easy. All the heights are equal to 1. All those heights are equal to 1. So I'm going to run some geometry now, and we're going to figure out what each of these regions adds up to. Okay, regroup in a second. Okay, so far so good. So running some mathematics on these bad boys, I got 32% for each of the middle sections. Now, some of you are thinking those should be 34. You're absolutely correct, but remember, we're missing some space up here. So they should be less than 34 because we haven't filled that curve in enough yet. We'll get to that. Promise, we'll get to that soon. So 32 and 32 is 64. I'm going to round these off to 15 each just to make the math easy. That's an additional 30. So 30 plus 64 is 94. And then we've got 2.9 and 2.9, which rounds up to 3, which is 6. So that should be 100, but then you're going to say, but Sean, you rounded both of these up. So it's actually less than 100, and you're correct, because these tails I haven't talked about yet. And I will not talk about them on this chalkboard, promise. But right now, this area, if I sum this area up, hang on a second, equals sum of those 3 times 2, I get 99.54. So if I use 6 regions, I get a total area of 99.54%. And that's cool. I'm missing about 0.5%. And some of that missing is because I haven't done these 2 extreme tails. But the other part of that missing is because these trapezoids don't really fit the curve perfectly. So what I'm going to do next is I'm going to make them fit more perfectly by, instead of gapping 0 to -1, 0 to 1, I'm going to gap not that, but instead I'm going to put halves in here. 3 halves, 5 halves, -1 half, -3 halves, -5 halves. So what you're going to see, and I'm going to add this in brown, is you're going to see, will brown work? Works pretty well. We're going to see the brown trapezoids fill in like this. And what you're going to have is now this, which is going to fit the curve much better, because we're going to essentially pick up some of that space that we didn't have originally. Same thing over here. If we come down to a half, you see what's happening? We're picking up additional space, and we will continue to do that the further out we go. So we're going to catch back up here in a second. I'm going to do the whole thing at once. I'm going to utilize these marks again, because those still exist. But I'm also going to pick up all the ones in between. So bear with me. Let me get caught up here, and we'll regroup. Whew. Okay, so the goof I made, and then of course these areas carry over here because they're equivalent. The goof I made originally, this is just more of a moral of a story than a mathematical one. I was using it because I was using an Excel spreadsheet to run the math on this, and I inserted some cells, and I had a formula that was updating automatically. And as I was writing these numbers down the first time, when I made that silly face, I realized that I goofed in the calculation down here. And I realized it because as I was writing these numbers, I think I got to here, and this was like 7% or something. I'm like, there's no way that can be 7. And these are too big, too. And so I guess the moral of the story is, as you use technology in your lives, don't become a slave to it. Make sure that the answers you're getting make sense as you go. And the trick was, everything looked good. As if you weren't looking at the context of this curve, the numbers are just numbers and they're going to float by. But thinking about it in context, I realized the numbers couldn't have been correct. So, I want to leave that in there as a mistake, because I think it's a good part of the learning process, is realizing that we all make mistakes. You've seen me make mistakes in class, and I will continue to make mistakes in class because we're human and we do make those errors. The important thing is talking to each other, talking to me, talking to you, and figuring out where those mistakes lie. Okay, anyway, so you see these areas, everything from 0.6%, 1.8%, 4.6, 9.3, 14, 9, and 18, 8. And then if you actually add all this up, and now this is what? There's twice as many regions, right? This is now 12 regions. And this comes in at 99.77%. So this is pretty phenomenal. We're beginning to creep up on the percentage that, quote-unquote, should be within 3 standard deviations. Now, we're never going to get this to 100%. Because this is not 100% of the curve. We're still going to miss this tail and that tail there. And with the next bit of this video, when we attack it with technology, you'll see how to actually get it to that point of of the curve, and how it will get you 100% using the next bit of integral calculus. But I want you to think about this before we go to the technology. Realize that we could break up this curve even better, because we still have gaps. We still have gaps here. There's always going to be gaps. So you can split them up by half and half and half and half again, and keep splitting and keep splitting and keep splitting. And calculus allows you to deal with that down to the, if you will, microscopic level, so that you've broken it down all the way. I'm not going to do it on the chalkboard because it would take forever, even though I've got a fairly quick way of doing it here, fairly quick. This is still going to take longer and longer with each additional number of subdivisions that I have. So we're going to go to the tech now. We're going to see how the tech allows us to speed things up quite a bit. So bear with, and let's go to the computer.